Good morning everyone. Myself N.Uday Ranjan Goud, working as Assistant Professor in Aeronautical Department in MLR Institute of Technology. So here I am going to teach Aerospace Structures subject, and in this we are having the first session, that is Introduction to Structures. So as you all know that for studying aerospace structures we should have fundamentals of engineering mechanics, engineering mathematics and mechanics of solids or solid mechanics, and followed by aerospace vehicle structures 1. So with these prior knowledge, and this aerospace structure subject becomes much easier. And coming to the course outcomes of this subject, at the end of this semester the students are able to illustrate the tension field and axial flow diagrams, and they should be able to explain the failure stresses in the plates as well as stiffened panels, demonstrate a shear loaded thin wall beams. So usually we will have stress strain displacement relationships as well as direct stress and shear flow system, shear center, twist and warping. And the next outcome is differentiate between the buckling of thin plates and the deflections due to bending. And the last outcome is the students are able to develop wing spars and box beams, probably tapered wing spar, open and closed section beams. So these are the course outcomes which the students should attain at the end of this particular subject. Now coming to the prerequisites, as we already told that the basics of engineering mechanics is very much essential, followed by mechanics of solids or solid mechanics, aerospace vehicle structures 1 and engineering mathematics. So here I am giving engineering mathematics because in structures most of the syllabus will be having the derivation as well as problems. So engineering mathematics knowledge is essential to solve any kind of problems in structures. Now coming to the introduction, thin plates. So the first unit we have thin plates, and so what is a thin plate basically? So a thin plate is nothing but a sheet of material whose thickness is small when you compare with the lateral dimensions. So the thickness is very small when you compare with the lateral dimensions, that is it may be the length as well as the width. And so such a plate forms a basic part of an aircraft structure, and for example area of stress can bounded by adjacent stringers and ribs in a wing structures or by the stringers or frames in the fuselage. So these thin plates are used extensively in the aircraft structures because of its advantage of being less weight and as well as more strength to weight ratio. So it's very important to know that the less weight is always a paramount design in the aircraft structures. We use extensively these thin plates in the aircraft structures because of its advantage of being less weight. So the weight is very less, that is the very first thing, and also it has got advantage of greater strength to weight ratio. So its advantage of being greater strength to weight ratio. Because of these two parameters, most of the aircraft structures they use thin plates. Next, now coming to the thin plates, so how the plates are being classified as whether they are thin or thick or intermediate. So there is a ratio called, here we have B by T ratio. Now if the thickness of the plate is between 8 to 80, that is the B by T ratio, if it is between 8 to 80, then these plates are regarded as thin plates. And if the B by T ratio is less than or equal to 8, so these kind of plates are regarded as thick plates. Okay, so if the ratio of B by T is between 8 to 80, those plates are regarded as thin plates, and if the B by T ratio is less than 8, then those particular plates we call it as thick plates. And if the B by T ratio is greater than 80, then probably we call them as membranes. Okay, so B by T, B is nothing but the width of the any plate and T is nothing but the thickness. So based upon these ratios, the plates are classified as whether they are thin, thick or whether they are membranes. And not only that, these thin plates not only used in aerospace structures, but they have got a wide range of applications. They may be used in aerospace sector, or they may be used in marine, civil engineering, automobile industries, because of the advantages of lightweight and more strength in the application. Now you are able to see the schematic diagram and as well as the thin plates example we have seen here. So these are the thin plate. Now you can observe here the thin plate, its width and length are sufficiently more, and when you look at the thickness is very small. Okay, so these kind of plates we call it as thin plates, and the schematic diagram is shown here, in which we have 3 axis system, x, y, z axis system, and also the thickness is being considered here as h, and you can see the plate dimensions are taken as A cross B. So the thin plate dimensions, it's taken as A cross B, and this particular dimensions we always take for the thin plate in almost all the derivations. Now approaches. Now these thin plates, and when they are exposed to either bending, shear or torsional loading, now how the thin plate behaves. To know that, we have got 2 approaches. The first approach is nothing but the exact theory based on the solution of differential equation. So this is basically the theoretical method what we have here. Okay, and we use the solution of differential equation, probably we call it as partial differential equation. And the second method we got energy method. Now in this energy method, as we know that this relies on the principle of stationary value of the total potential energy of the plate, and here we know that the total potential energy is equal to the summation of strain energy capital U and the potential energy of the applied loading capital V. Okay, so energy method, and when we use this energy method we should find both the expressions like total strain energy stored as well as the potential energy of the applied loading. Now when you look at the first one, exact theory, so here we are going to see the thin plates which are subjected to bending, and the plates subjected to bending and twisting, plates subjected to distributed transverse load, combined bending and in-plane loading. All these derivations we are going to see, and we are going to develop some equations which are very useful for solving the problems. Right. Now assumptions. Now the thin plates assumptions, most of the time we give assumptions for beams or columns. Now the similar kind of assumptions we will consider here. The first assumption, if you look here, the material of the plate is elastic, homogeneous and isotropic. The second assumption is that the plate is initially flat, and the third one is the deflection of the mid plane is small when we compare with the thickness of the plate, and the fourth one, plane sections remain plane even after bending, and the fifth one, since the displacements of a plate are small, it is assumed that the middle surface remain unstrained after bending. So this particular one, the fifth assumption, we call it as neutral layer. Okay, the middle surface is being unstrained even after bending. We call that layer as neutral layer, and an axis passing through all such layers is called as neutral axis. So we consider all these 5 assumptions in the thin plate derivations. Okay, so this is the introduction for aerospace structures. So as you are learning from the first unit, everyone should go through the basics of engineering mechanics, solid mechanics, as well as aerospace vehicle structures 1, and in mathematics, and especially in mathematics the differentiation and integration you have to go through, because here we are going to do normal integration only, and as well as normal differentiation. So without this differentiation and integration we are not going to get much easier in the derivations. So it is better to go through the fundamentals of mechanics and solid mechanics before we start this subject. So that's all from the introduction class. Let's look forward to the next session in the next class. Thank you.